All right, a little short video on integrated rate laws. And this topic is the problems don't really inspire like the true nature of it, but it has large ramifications like cleaning products, like how quickly they act and break things down, and or how long like afterwards, right? After you spray it and then you want those cleaning agents to break down and be recycled back into it. So it's a balance between those strengths. And then you can apply the same principles to a lot of different products and, things like that. So kind of cool stuff. But at the end of the day, what are we trying to solve? On the website, you'll find examples where mainly I focus on finding the concentration later. So you're given a starting concentration and a rate constant and told what kind of order, and then you just have to solve it. And these are classic plug and chug kind of problems. And and so then you just have to know the different formulas for the different zero, first, and second, and so on. Then I have half-life problems. And there's another set I've worked on, but actually I don't have it linked in there. And so, but maybe I'll get it uploaded soon. So onto it. So first, I take this figure from Kim Libre. That's a great source if you don't go there. But nice summary table between zero, first, and second order, and just knowing the basic nature, saying the rate law of it, and so and then hopefully you're able to determine the units of the rate constant, and that's one thing that's unique for rate law is because it's proportionality constant relating that concentration to the rate depending on that power, and so the units change based on that. All right, and so here's the big picture, is that with zero order, we have just the concentration at A equals minus KT A naught, and this would be Y. So if we graph this, this would be Y, and this would be X, and that would give us our linear form. On first order, it's ln A. So we start with A, we take the ln A, that gives us first order. And notice we have ln A here, and we have ln A naught as the intercept over here. And now on second order, it's the other way to modify this. It's the inverse. So inverse of A here and inverse of A naught. The other difference is that in zero and first order, they're minus KT. In second order, it's plus KT. There's a relation between half-life. I don't like these types of calculations because it just, like, this is the full, if you want to solve for the concentration at some time later, which is the exact problems I put on there, you can actually work backwards and go back in time like physics. I don't put those examples because it's just focused on you being able to do the calculation with the different ones. And so now we can see the slope. Again, like we focused before, the slope is minus. K is equal to minus slope because these are negative, and here it's equal to plus slope. So, yeah. So here's an example problem. So the rate constant for the first order decomposition of cyclobutane at 500 C is this. So this 500 C isn't useful. It's just defining that the rate constant is dependent on time, and that's what the Arrhenius equation relates, similar to the Clausius-Clapeyron. So that's why it's always specified. It's just because at that temperature, this is the rate. If we cool it down, it slows down. If we heat it up, it goes faster. So we always have to dictate it. But you don't use that number in the calculation. How long will it take 80% of the sample to decompose? And so if you look at it in the solution on that website, then it gives you a different form, all right? And this can be a little surprising, but all they're doing is rearranging. Then we had A and we have A naught, and when we move it over, if we go back to the other slide here, it's first order over here. And so we would subtract over A naught and have ln of A minus ln A naught equals minus KT. And so getting rid of this minus, making this plus would flip these two. And then what is taking advantage is an identity. So when you subtract the natural log of it, it's equal to ln of A over A naught, all right? Or vice versa, because it flipped it and made it negative. All right, so that's just the algebraic kind of rearranging I don't know if you see natural log in algebra, but that's all that is. So it's not another equation. It's this just uh, modified. The thing is, at the end of the day, you can plug this in your calculator because you know the starting. Oh no, it said 80%, so you don't know that number. But so you know this number in this one, and you should know this number, and so you're solving for time here. So you can actually just plug it in and don't even have to do that math of rearranging and solving. And so now we'll just go forward again. And so how long will it take 80% of the sample to decompose? So this is a great kind of problem because you can just make a number up. And so the thing, so you have kind of two options. Do you use 80 or do you use 20? So if you start at 100% as A naught, and then we go forward, when 80% of it's decomposed, that means you only have 20% left. All right, and so it doesn't really explain it here. It's kind of in here in this wording, but if you look at it, but they do have these help buttons, which I think will help you with it. So good classic problem that we have. I don't have any of those examples. I give you a rock hard number, but if you look in some textbooks, they definitely have examples like this. So take a look and see that you're able to solve this. And you can see with this equation, you can solve for any time, any concentration. That's why we use it in a little bit of work, but not too demanding. There's some other examples here. So how many days will it take 90% of the iodide to in a 0.5 molar solution to decay? And so here again, the 0.5 is actually doesn't matter. So you can calculate, or we can just start with like 100% and go down to 90 and do that kind of thing too. So you can check and see that you get this number. Here, then looking at second order, they give you a rate constant, and here they just say under certain conditions, meaning not telling you the time. If the initial concentration is this, what is the concentration after 10 minutes? And so again, you have to remember second order. You remember that kind of modifier. Is it just A? Is it ln A or inverse A? And so hopefully you lock that in, you have that, and it's inverse A. And so another one is minus minus plus. Minus for 0, minus KT for first order, and plus KT for second. Now that you have this, then we have everything we can easily solve then for the inverse. And one kind of key thing to always pay attention to those units, because that units is a guide that this needs to be flipped. When you solve for it, you're solving for inverse A, so the units don't match up where concentration has the units moles per liter. So if you get here and you have that number, just take the inverse, flip it, get the units right, and the number will match, and it should work out perfectly. The last one I'll have here is the problem they have for half-life, and they go on and convert between half-life and rate constant and solve for that. I don't ask those types of questions, but I do the same type of calculations using half-life in nice intervals. That's what we usually use it for, approximating. And so the key thing problem I would like to have is to really, like the first one, if given the amounts, is it focused on how much is left or how much is lost? And there's that kind of inverse relationship between them. And so only what's left on there right now is what's left, but plan to add how much is lost and then have you think about it. So if initially you have a 1 molar solution, after one half-life, you lose half, and then after another half-life, then you lose a half of that again, and it just keeps repeating. So you can divide it by 2 and follow. But what I tend to do is think about it like this. At 0 times 0, we have 100%. After one half-life, 50. 2, we have 25, and we just keep doing the same thing. So it doesn't matter how much I start with. Then once I know how many half-lives have passed, then I can just multiply by that number. Okay, so hopefully you found this useful, and then I'll try and get it all uploaded for you.